When light strikes a metal surface, it can knock electrons right out of the material, violently ejecting them into space. This interaction is known as the photoelectric effect. Observations of this phenomenon were a primary catalyst for the transition into quantum physics, as classical theories couldn't explain how light and matter exchanged energy. To study this, researchers used a controlled environment, two metal plates, an emitter and a collector, sealed inside an evacuated glass tube to monitor electron behavior. The goal was to find the exact rules governing this microscopic collision. Specifically, physicists needed to identify which physical properties of light controlled the speed and energy of the escaping electrons. If you were standing in that lab and wanted to give those ejected electrons a massive boost in kinetic energy, what dial on your light source would you turn? The intuitive assumption is that you just make the light brighter. Cranking up the intensity should hit the metal with more raw power, kicking the electrons out with more speed. But the experiments showed a different reality. Increasing the brightness doesn't speed up the individual electrons, it only ejects a larger quantity of them. Double the brightness, and you double the electrons flying off the plate, but their maximum speed stays exactly the same. To actually change the energy of those electrons, you have to change the color, or the frequency, of the light. In the photoelectric effect, light intensity dictates quantity, while frequency dictates energy. To understand why, we must look directly at the experimental data used to measure invisible particles. Measuring this energy presents a challenge. You can't point a radar gun at a microscopic, invisible electron flying across a vacuum to check its speed. Instead, researchers used a method called stopping potential, denoted as V0. Think of the stopping potential as an invisible electronic hill that the escaping electrons are forced to climb. By applying a negative voltage to the collector plate, researchers can create a repulsive force that pushes against the incoming electrons. This retarding potential forces them to slow down as they're crossing the tube. By gradually increasing this negative charge, you eventually hit a precise point where even the absolute fastest, most energetic electrons are stopped and turned back. This voltage point allows us to calculate the maximum kinetic energy of the particles. Finding this specific stopping potential provides the definitive, measurable proof of how much energy the light waves actually transferred to the metal. This chart maps the photoelectric current on the vertical axis against the collector plate potential on the horizontal axis. We will keep the brightness of our light constant, but run the test multiple times using different light frequencies. When we shine a relatively low-frequency light onto the plate, we get this first curve. Notice exactly where it hits the negative horizontal axis. That intersection point is the stopping potential required to halt the electrons generated by this specific frequency. Now look what happens when we repeat the experiment with higher frequency light, moving from yellow to green to blue. The new curves, nu2 and nu3, shift outward. It takes a much stronger, more negative stopping potential to halt these faster electrons. However, look at the top right. All three curves merge into a single horizontal line, called the saturation current. This is the point where all emitted electrons reach the collector. Since our light brightness stayed constant, this total current remains the same regardless of the frequency. This data confirms a specific rule. Higher frequencies of incident radiation always result in more negative stopping potentials. The graph demonstrates that light frequency, not brightness, is the master dial that controls the maximum kinetic energy of the electrons. Plotting these stopping potentials against light frequencies reveals a perfect upward-sloping straight line. This proves an electron's kinetic energy increases linearly with the frequency. But the most important detail is exactly where this line meets the horizontal axis. This intercept is the threshold frequency. It is the absolute minimum frequency, the baseline color, required to pry an electron loose. If the light doesn't reach the specific frequency, no electrons are emitted at all. This cutoff point means the photoelectric effect can completely shut down, regardless of how much light you use, which led to a new understanding of how light is actually structured. This relationship leads to a direct physical comparison that illustrates why light intensity cannot compensate for a lack of frequency. Imagine a beam of red light so intense it is blinding. Because red light sits below the metal's threshold frequency, absolutely nothing happens. You can shine this beam for hours and the electrons will remain locked inside the metal. Contrast this with a tiny, dim beam of high-frequency ultraviolet light. It instantly ejects a stream of high-speed electrons. For your exams, remember the distinction. Above the threshold frequency, kinetic energy rises linearly with color. Below that threshold, emission is impossible, no matter how bright the light is. In the strange quantum realm, the specific color of a single light wave completely determines its physical power, proving that when it comes to electron energy, frequency is the only thing that matters.